Okay, so I see that we are ready, and we could, I think, invite our first speaker. Just a huge round of applause for the Ole. And yeah, I can see him. Hey, hello.
So I think I should start now. Thank you. I'm doing a bit of a blind flight here today, sorry. Welcome to my talk. So I want to share why Go is becoming so popular. So what's interesting about it, what sets it apart from other programming languages, and in the end, how does it handle complexity? What can you do different there? Since this is usually the end game, kind of. Right? Every project is great until it becomes really complex. And so let's take a look at that. Yeah, a bit about me. I've been doing lots of software development many years, co-organizer of the Berlin Go meetup, and now let's start to go into programming. This is a little Go program. So every Go program lives in a package. The main package is where it all starts. So function main in a main package is where the entry point for every program is in Go. And so what we want to do here is reading a file. It's quite simple, straightforward. There's a read file function that you can call, give it the name of the file to read. And then you get the content back plus an error, possibly. Then you handle the error. And finally, you can do something with the file content. We just print it here again. So what does it all tell us? This is quite boring, right? Because you can do this in almost any programming language, probably. JavaScript is a bit of an exception because it offers only asynchronous IO, which is great somehow because it allows better scaling. And it looks a bit between a scripting language and a traditional compiled language. Not many types would have to be given, but yeah, nothing too special. But what would be cool instead? Asynchronous IO, as JavaScript has, would be great because it allows for higher scalability. And of course, you want to use the time while waiting for IO to perform other tasks. And no garbage collection breaks or very, very short ones. That would be great. And Go is using garbage collection, but it is indeed very short. And Go is doing all of this behind the scenes. And this is the kicker about Go. It looks like a boring, simple, straightforward language, but under the hood, it is doing all this cool stuff. And this is why you can do high throughput, low latency servers with Go. And they are still quite maintainable. We don't need callbacks or reactive libraries or anything special. And the same goes for network I/O, of course, any kind of I/O. And yeah, as I said, this allows high throughput, low latency services. Go is very simple in this way, right? And because this is one nice thing, the foundation for Go becoming the language of the cloud, but you as well need some resilience, right? And this can be very tedious. And with Go, it's a bit easier. I quickly go over here. So when you do a Google search, like you want to implement that, you want to search in parallel for web results, for image results, and for video results. And you want to do that in parallel. So you start 3 Go functions, Go routines in Go. So these run in parallel. And whenever one of them is stuck on some I/O, one of the others would be run on the same processor. So even with a single processor, this can save you a lot of time. And you want to have a timeout because you want to hand back results quickly. We chose here 80 milliseconds. And you want to have 3 results, so loop down to 3. And every time we get a result from the channel that is written in one of those, we would append it to the results that we return in the end. And in case of a timeout, we say, sorry, timed out, and return the results as they are until then. And if the loop ends normally, so we got all 3 results, it's returning immediately as soon as it got all 3 results, right? So this is a way to do this. And this first is interesting too. You want to have multiple instances, since sometimes the server can be slower, there can be some problems. And so companies like Google have multiple running in parallel with the same content. And so for web search, we have got 3 replicas here and 2 for images and videos. And the first result is taken. And this is implemented in a quite similar and simple way. You create a communication channel, then set up the Go routines that write to the channel, and for each replica, sending the query string into it, and then it sets up the Go routines for each of these replicas, and the first result that appears on the channel is simply returned, and the channel is cleaned up automatically. And this is all you got to do, and you got a quite resilient and stable system already just by this. And yeah, more resilience patterns, timeouts are handled with the help of the standard library nowadays, so you don't have to do that much at all. And others are implemented usually in open source libraries. So they all work in a similar way, usually no logs, no mutexes or whatever things you usually have to do in other languages. Other features in Go. Now we go into the direction of complexity handling a bit. So layers of abstraction, we try to avoid them as much as it makes sense. So we think about in Go, what would be a good API, and underneath we try to avoid layers of abstraction and make something nice to use, but not additional layers of abstraction, because it is some pattern. So we try to avoid these famous patterns. Yeah, most of the standard libraries only like 1 to 3 calls deep. And I never had to debug more than 5 calls into any dependency that I used. And of course, in business logic and big servers, you can still have more, but it's try to avoid it. Most functions fit on a single screen, so you don't pay by not having many calls deep, but huge functions or so. You can still understand them quite quickly. They are not like 3 lines often. Sometimes they are, but often they are more like about a screen size. And even the heart of the runtime system, the switching of the Go routines, it's quite simple. It's about 1 screen full of code, bit dense, but it is possible to understand it, how this is done under the hood. And the whole function is a bit bigger, at least 2 screens full, because of some special edge cases and setup and so on, but it's not that huge. And yeah, bugs and dependencies can be discovered quite easily, since you can simply step into a code and find something. And yeah, you can fix it and then hand in a pull request, and this usually gets accepted quickly. I just did this 2 weeks back. So, but in the end, there is no silver bullet, of course, since complexity is the huge thing you have to do something about. And yeah, all the neat code in the small can't save you from when it's getting really big. But simplicity is a North Star, so we try to shave something off of it wherever possible and go. And we got this proverb, do less, enable more. So we, instead of handling a lot of edge cases in a function, we rather do the straightforward things that are the heart of it, and then have a Lambda, a callback function that does all the special handling then. And so the function itself does less, but enables more, because this callback function can do way more special things than we could implement easily in the function itself. And yeah, let's take a look. How does this scale? So in the old days, we had only monoliths, right? It was one deployable unit. Yeah, operations insisted on it. Well, never been questioned really. And yeah, these systems grew without bounds. Many still remember, suffer from it, usually becoming a big ball of mud. So quite unmaintainable, huge thing. And this looks something like this, the crazy thing in the middle. It's really hard to understand anything there, or like that. It's even more wild, and yeah, you don't get a real chance to understand anything. And I have to talk a bit about Java, since this is the language that has been most used about it. I've been using Java for almost 20 years myself, so I know still a bit about it. It allows circular dependencies between classes. Of course, for some programming patterns, you need them really. And this is a big thing. It allows circular dependencies between packages too. And packages are the biggest structure we have in Java, really. And when circular dependencies are allowed there, it's hard to follow and give it structure. The compiler doesn't help us much there, unfortunately. And yeah, between projects, it's not encouraged really, and it's rare. I think it doesn't bite one really, but I don't think it's really prevented either. So yeah, how can we handle tools? Complexity the traditional way. You can use structural analysis, so IDEs are quite good for that. Rename classes, all these refactoring things, right? Move functionality around, extract methods, and so on. Big companies have their own specialized tooling. Google is really famous for this. And now we get microservices, right? We don't want this huge thing anymore, this big ball of mud. Now we have one system with 1,000 deployable units sometimes. And yeah, this is the thing we have to do now with DevOps and cloud, and I've seen it rarely being questioned. Systems still grow without bounds, and now it becomes spaghetti architecture instead, right? So no spaghetti code, because the services themselves are too small, but inside, outside, the relations between all the services are really a lot still. And one part, let's see why and how things are split up in microservices usually. So one good reason is one part must not take down another one, right? If I have a big monolith and there is one small side part that goes down, causes a segfault. It would take down the whole monolith, and then this would be really bad for resilience, and we don't want that, of course. That's a good reason to split. Another one is if some parts have to scale widely differently. Often it's you got a front end that has to scale for millions of users, and then a back end that has to scale only for very few users, like 10 to maybe 100. And this is something that makes sense to take apart. Then you can install the front end separately on many servers and the back end only on like 2 or so. And parts are really independent. Yeah, if it's getting really big and you got some parts that are truly independent, well, then please take them apart. But you don't have to, right? And another reason often used is to prevent this spaghetti code of this. They don't want this big ball of mud. But maybe that's not the best reason, right? There it's getting a bit vague. Maybe you can achieve this in a different way. And another reason is because it's too cool, because everybody's doing it, because you want to be modern too, and so on. Yeah, this is maybe the worst reason, right? If you don't have a real reason for it that really applies to your context, maybe this is not such a good decision then. Let's take a look at an example. So that tries to use cool new stuff, implement services in the CQRS pattern because it should scale better and helps us split services even more and nicer and so on. And yeah, so let's take a look what this looks like. Here we are. So when we got a microservice, we got lots of services. So, and here we got services like for bank transfer and a command and a query service. This is the CQRS pattern. You split the write request, these commands, from the read request, these queries. And it's a bit like I said between front end and back end, right? The front end is often the one that is doing the queries, the read requests, and they have to scale a lot, like looking at products in a catalog, like searching for something on Amazon or so. And then the command is where you really place the order. This is doesn't have to scale so much, right? This is much rarer. And so you get difference there. And you split up everything like that. And then you get a lot of services quickly. And they all look quite uniform usually, right? You got one executable, you need to access the database a bit, you need to message around, you got a service package that contains the business logic, and yeah, you need HTTP, so web access, where you implement the HTTP routes that where you receive the calls from the UI. And so it just doesn't give you a hint how this is structured. These are all independent projects, and it's really hard to find out how a complete flow, purchase flow in this shop example, how does this really work? You can guess, but it's really hard to find out, and after a while, you usually get some additional services here and there that are not that obvious from their names, where they are and how they are used and so on. And the only way to technically find out is either looking at all the messages and grabbing around there for who is using the message type that you are interested in. Or there are these systems like Jaeger and so on, where you can observe what's happening in real time in a production system or so. But then you have to set up a lot of infrastructure for that. And this is way slower than in the old monolith, where you could just with a mouse click ask for all the users of something. And so this can give quite a headache already. Let's take a look what other things can happen there. Yeah, this is really a service diagram from Uber. So I have to admit, it's impossible to find class diagrams, traditional class diagrams of monoliths. And so I took this service diagram from Uber. It's from Introducing Domain-Oriented Microservice Architecture. But it still stands, right? You don't understand much what's going on there. And this is from Monzo, their famous blog post, How Does Monzo Keep 1,600 Microservices Spinning? Go Clean Code and a strong team. Yeah, with them a very strong team. It's really hard to find your way around such a system. And yeah, the downsides are, as I told you, the providers, especially users of data, it's really hard to find, to know who are the other systems I'm interacting with, really, without it being obvious. And updating dependency with 1,000 microservices is even harder. You can do it in many little steps, which is nice, but it's really, really hard. It's a lot of work, very tedious, and usually they diverge. So you maybe agree on a set of dependencies, like libraries you want to use everywhere, but every service is using kind of a different version of it after a while. And this can make it impossible to merge back something together again. This is really, really difficult. And moving functionality around, this is something your IDE would do for you in a traditional monolith. But here, you can just copy paste. They are completely different projects. There's no way you can have an IDE do this for you. And cutting services in a different way is practically impossible. The only thing that I've found once that has been working is throwing all the code together, first to a monolith, and then split it up again. And this is, of course, something really, really crazy. And you probably never do it. Most companies simply declare it's okay, it's not that bad. You don't have to cut it in a different way. And so what might be a future way to go is a monorepo with some services. So you have one system with some deployable units. So you still got some of the downsides of a monolith, since you have a single repo, but not that much, since you have multiple services for resilience, for scalability, and if things are truly independent, but not just because it's possible. And yeah, DevOps Cloud are quite great for this. And of course, systems still grow without bounds. But how can we prevent a big ball of mud now? So let's take a look for how Go can help us with that. So generally, Go has been engineered for scalability, and the packages are made for encapsulating functionality. You can't break into a package later. Package is a unit of compilation, and you can't change it afterwards. Dependency cycles between packages aren't possible. This is one of the big things, I think. This is the similar to Java. This is the biggest unit you got in the programming language itself. but you only are allowed to have a hierarchy, and cycles aren't possible. And you can have additional tooling to prevent more cycles or more dependencies that you don't want to have. And let's take a look how this can be done. So I got a tool that I want to show you quickly. You can configure it. You can have two packages. So I say everything under X is a tool, which is the standard in Go. And then I have an additional package entities that is tools that will be used anywhere. And then I have something in between, which can be used almost anywhere, but is using the tools itself. These in the front end, I want to handle customers almost everywhere. In the back end, the catalog data, I want to handle almost everywhere. And I want to prevent a huge package. So I say the maximum size allowed is 1024. The tool tells you how big your packages are, and then you can adjust it. And it's measured in a measure that's independent of formatting or splitting up into multiple files or something. It's measuring packages and not how many comments you got or something like that. It's independent of that, not simple lines of code. So it's really measuring complexity. And so how does the project look like now? So we got the backend and the front end. As I thought, you might make sense to split it like that. So the front end, that's the shop front end as an executable. It handles customers, which are used a lot around the system. It's doing the payments, main transfers, credit card, PayPal, vouchers, and of course, a shopping cart. Something is missing in here, right? We don't have the catalog. We can't look at the products that we want to sell on the shop. How do we do this? The catalog is part of the backend. And well, it makes some sense since it's changed in the backend. It's you can add products there, you can even remove them, and then nobody can buy them anymore, and so on. So it's owned by the backend somehow, but you want it to scale with the front end. And how can we achieve that? Well, the backend has two executables. One is the normal backend of the shop, where that contains all the routes. And then we have a back for front. This is the backend part that is really for the front end. And this allows us to package only the routes that are needed for the front end, this reading of the catalog. And and then have it deployed with every front end together and let it scale together with the front end. So this can scale quite nicely, and still we got the code together with the rest of the backend code. So it's easy to change something in the reading part of the catalog, and it's not somewhere completely different. And I make a small change for the write part, and I forgot about the read part or something like that. It's not a completely different package. It's easy to do. So this should be good for maintainability. Besides that, we got recommendations and statistics for customers and products. And yeah, this is the whole system. It's not too difficult to understand. And I think you get these three executables in the end. It's not too big, and you can still find your way around there. And yeah, this is something that might be a good compromise. So let's take a look at this tool more, the spaghetti cutter, because there it helps with this spaghetti code, as I told you already. So next to this configuration, you get this dependency table out of it. It's automatically generated for you, and it tells us, for example, this X logging is a tool package, as we configured it like that, and this is imported by literally everything else, right? This is imported everywhere, so it's a tool package that's okay, and these entities are imported almost everywhere, right? They aren't needed for these recommendations from external sources and some other things, but they are used a lot. And we got the executables that import a lot of things. Yes, the main packages, that's their role to gather things together and plug them together. They are big, but they plug all the stuff together. And this is fine. So you can see the structure here. And even if we wouldn't know what kind of packages is, we can find out this way, right? These things that are imported a lot, but aren't importing anything themselves. So I can't find them even on this site. They are tool packages, right? And so on. So I can generate such a graph at first, and then I can just declare everything here as a God package. That's what we didn't use yet. And God packages can import anything, are allowed to do anything that the compiler allows. So no circular imports, but beyond that, they can import anything. Only the main packages are God packages by default, and I can declare anything to be that. It's a simple, do a star instead of a single star, and then I got everything. And I can look at the graph and then see, these are tools and so on, and start giving it a real structure. And then I can rather quickly come up with something that's nice. And here I got some additional allowances. So email package is used by the user service to send lost password request emails and so on, and similar for customers and payments. When you successfully paid, you done the purchase, you get an email, of course. Things like that can be done, and it's not too much that you have to do. Usually around a screen full, for big projects a bit more, but it's quite easy to understand, and for new people it helps a lot to get into a project and understand how it's structured. So you can break up this monorepo or monolith a lot like that, and it can't work for microservices, unfortunately. I don't know how to build something like that for microservices. That's the problem. So let's see what we get in the end. Yeah, this is an open source tool, ready to use. I want to release version 1 in February, just some tests missing. It's a command line tool, so for CI/CD pipelines, development machines. You can use it locally, of course. Prevents code with error messages, return code, not zero, and it gives you this automatic documentation. So it's pressing the red button when something goes wrong, right? And yeah, let's see in the end. Think the Go programming language is encouraging simplicity wherever it can. Microservices are simple themselves, but overall you pay a high price. And reasonably sized services would be a great compromise. And tools like Spaghetti Cutter can help you preventing spaghetti code. And please enjoy your pasta in nice bites. So, thank you.